So, the chapter 21 homework is due on Friday, the 26th. The chapter 22 homework will be due on the 3rd. The chapter 121 quiz will be on Wednesday, the 24th. That's this Wednesday. We're going to finish chapter 21 today. So that's the case. We have a lab today at 1. And the Pangea lab is due today. But you can turn it in during the lab. You don't need to turn it in now if you don't want to. So we were talking about rocks and igneous rocks. So dark, low silica rocks are denser than light colored high silica rocks. We'll be looking at rocks today in lab, identifying them. That will allow you to see the differences at some level. And continental plates are composed of less dense high silica rocks, and therefore they stand higher above sea level, while oceanic plates are composed of more dense low silica rocks, and therefore rest lower, usually below sea level. And medium silica rocks are usually called andesite. So here's a table showing common igneous rocks organized by their composition. If they're high in silica, they're light in color, they're less dense. If they're extrusive with small grains, this is rhyolite. If they're intrusive with large grains, this is granite. Granite is more common than rhyolite, because granite makes up things much akin to granite make up most of the core of the crust. If they're medium, they're andesite. If they're extrusive, and diorite if they're intrusive. And if they're low, they're dark in color. They're basalt if they're extrusive, or gabbro if they're intrusive. And basalts are more common than gabbro because much of the oceanic crust is created at oceanic spreading centers, which are volcanic and create extrusive basalts. Now, ocean crust, continental crust. Overall, continental crust is less dense and thicker than the oceanic crust, which is more dense and thinner. When large igneous rocks form underground, they're called plutons. So this is a large body of intrusive igneous rock that forms below the Earth's surface by the solidification of magma. And plutons are classified according to 2 criteria: their size and the shape of the intrusive rock body. How big they are and what their shape is, their size and shape, and their relationship to the surrounding rock. Do they just sit between layers, or do they cut across layers? That's sort of the idea. So a pluton is said to be discordant if it cuts across the grain or layering of the surrounding rock. So these are things like batholiths, which are really big, large structures that cut through a bunch of layers of rock, and dikes, which are thin things where magma filled along a fault or a joint and cut through a bunch of layers, forming a thin, sort of more vertical sheet. And they're concordant if it's parallel to the grain and the layering of the surrounding rock. These are sills, which are horizontal sheets in between the layers of rock, where the magma oozes between the layers, and laccoliths, which are magma goes between the layers, but enough of it gets in that the layers bulge up and blister. So here are some examples. Here's a volcano. Here's a sill. Sill is where it goes horizontally between the layers. Dike is more vertical, cutting across the layers. If you fill up between the layers, but fill it up like a big blister, that's a laccolith. It bends the layers up above it. Here's an exposed one on the surface. The vertical fills are dikes, and this big structure here is a batholith. So batholiths are large, exposed, discordant, intrusive igneous bodies. So By definition, a batholith has to have an exposed area of at least 103 square kilometers or 40 square miles. They originally crystallized slowly at great depth below the surface of the Earth, and they only become exposed when powerful forces push them up or when a very deep canyon is carved. A dike is a discordant intrusive igneous body that's formed from magma that fell to vertical or near vertical fractures. A crack that fills with magma which solidifies and it's more or less vertical. Since fractures are narrow, the filling intrusive igneous material hardens into a thin vertical sheet of igneous rock. So we have a thin sheet of rock going up and down. And the size and extent of individual dikes is quite variable. It depends on the dimensions of the fractures they fill. Dike is also a term for a structure you can build to that's like a mountain, which is where the term comes from. Sills are like dikes, except instead of filling a vertical crack, they go between existing layers and run horizontally. So these are sort of flat sheets of igneous rock that formed between layers of pre-existing rock. And laccoliths are also between layers of existing rock, but enough material is pumped in at pressure to bulge up the rock above them, creating noticeable blistering. So sills are thin, laccoliths are thick blisters. Now, if molten rock comes to the surface, you get a volcano. So a volcano, there's several types of volcanoes. It's a hill or a mountain that's formed by the accumulation of lava and volcanic rock fragments that get ejected through some vent in the Earth's surface. And there's three basic things that are ejected from active volcanoes. They are gas. So there's various dissolved gases in rock. So carbon dioxide, water vapor, various sulfur compounds, things like that. Lava, molten rock, and solid rocks. Volcanoes will spit out chunks of rock. So as a volcano erupts, you can get gases, lava, solid rocks. You can get gases flinging lava high in the air to turn into fine ash, things like that. Come on, load. Oops. Just gonna say. Melting molten rock rises up to the crust. incredibly destructive. So generally gases are always coming out of volcanoes. Some volcanoes will plug up, build up pressure, and have sudden releases when they explode outwards. But in general, there's a constant, steady release of volcano from gases from its entire life cycle. These are mostly water, actually. Mostly water vapor with certain amounts of carbon dioxide and hydrogen sulfide, and there can be some other gases as well. And lava comes out of volcanoes in differing amounts and varying viscosities. Some volcanoes have very thick lava that is sticky. They tend to erupt explosively, while other volcanoes have very thin, easily flowing lava, and they erupt more quietly. These are places like Hawaii, Iceland. Their lava is thinner and flows more easily. Some volcanoes emit large volumes of solid material known as tephra or pyroclastics. And this can be expelled in almost any size, varying from like ash and dust to like boulders. Tephra includes material that's originally injected, molten, and hits the ground as solid. So this includes things like a lot of certain types of volcanic ash is cooled little droplets of lava, and also things like lava bombs. And one of the more dangerous things you can get is something called a pyroclastic flow, where you get fine ash propelled high into the atmosphere, and you get a big cloud of ash and rock and hot gas, which gets top heavy and then collapses. And you get a flow down the side of the mountain of ash and dust and hot gas and things like that, which can travel very quickly, is quite dangerous because of that, and is actually more or less what buried Pompeii. So you may have heard of Pompeii, it's a famous place to buried by a volcano. That eruption, Pompeii was hit by the pyroclastic flow, but not by the lava. Nearby Herculaneum was hit by lava. And Pompeii was a little slower. Yes. So there's two basic styles of eruptions. You can have a peaceful eruption where a volcano sort of steadily releases lava. These tend to be volcanoes that erupt for a longer period of time. They have thinner, less viscous lava, which is more basaltic. And you can also have an explosive eruption. With an explosive eruption, lava is more viscous. It has difficulty flowing, so it tends to plug the vent until pressure builds up enough to, break the plug out. And that means that eruption is incredibly violent, because a steady, continuous flow is much more peaceful and much less dangerous than a sudden, violent release of pressure. Peaceful volcanoes spew lava. They can end up spewing lava for decades, like Kilauea in Hawaii, which has been more or less, it had an eruption that lasted decades. Then it cut off recently and then restarted after only a couple of years. It more or less has been erupting my entire life. There's been a couple of deaths, but it did have an eruption that lasted at least a couple of decades. That's low viscosity eruption. Or you can have sudden violent eruptions like Mount St. Helens, which blew the top off the mountain, or Mount Tambora in 1815, which threw up so much volcanic ash and dust that it caused the summer the next year to be called the year without a summer. And you get things that cause like tsunamis and stuff. So magma viscosity, it turns out, is dependent on two factors: temperature and silica content. It turns out they're also related. So low temperature magma tends to be high in silica content and high in viscosity. High temperature magma is low in silica content and low in viscosity. So in general, magmas that originate deep within the earth have higher temperatures and flow more easily and are lower in silica content. The higher the silica content, the higher the viscosity. In general, magmas that originate in shallow depths have a higher silica content. So high silica content, high viscosity, low temperature, high viscosity. These tend to go together. And low silica content, low viscosity, and high temperature, low viscosity, these also tend to go together. So, some examples. Rhyolitic magma has a low temperature, has a high silica content, and leads to violent eruptions. This you get in oceanic continental subduction zones, like Mount St. Helens. Andesitic has low to moderate temperature, it has medium silica content, and it is moderately violent to violent eruptions. This you get in oceanic continental subduction zones or volcanic island arcs. Some of these volcanoes you'll get, they alternate. Sometimes you can get volcanoes that will alternate between more peaceful eruptions and more violent eruptions. And this actually allows for the building of the biggest volcanic mountains, because the violent eruptions will throw out a lot of tephra, and the more peaceful eruption will glue it in place. And you can get really steep, tall mountains. And then basaltic, these have high temperature, low silica content, they have peaceful eruptions. They happen at divergent boundaries or hotspots, like divergent boundaries like Iceland, or hotspots like Hawaii. Peaceful eruptions involve basaltic magma. Basaltic magma comes from deep within the earth, and therefore it is hot. They also have relatively low silica content, so they come out low viscosity. They flow easy. And the combination of high temperature and low silica content, basaltic magmas flow easily, resulting in peaceful eruptions. They also have less water dissolved in them, because they come from deeper in the earth. Most basaltic eruptions occur in two distinct settings, either at divergent plate boundaries, like Iceland, or in isolated areas as a lithospheric plate moves over an unusually hot stationary zone in the upper mantle that's called a hotspot or a mantle plume, like Hawaii. And hotspots appear at the surface as a line of active, dormant, and extinct volcanoes. So there's the Hawaiian Islands, and the Emperor Seamounts are this continuous series of volcanoes that formed over the past 70 million years as the Pacific plate moved over this hotspot. So rising magma from a stationary hotspot in the atmosphere forms volcanoes as the Pacific plate moves slowly over the hotspot. This is how we get the Hawaiian Islands and how the older Emperor Seamounts formed. So the big island of Hawaii is the youngest of the islands of Hawaii, and as you go along the chain from there, they get older. As you continue on, the mountains move underwater and even older. So here is a short video about how hotspots make structures like Hawaii. So this is about how Hawaii formed.
Hawaii sits in the middle of the Pacific Ocean and nowhere near the edge of a tectonic plate where volcanoes are usually found. So how did the island chain form with all of its volcanoes? The island chain is located over a hotspot fueled by a mantle plume of heated rock. Solid rock at the bottom of the Earth's mantle is heated by the planet's core. That hot rock slowly rises and pushes up the crust, forming a bulge. Under that bulge, some of the rock melts into magma. Magma makes its way to the surface through cracks in the crust. Once it's above ground, it's known as lava. Hawaiian volcanoes produce lava flows made of melted basalt, which is more liquid than lava produced by more explosive volcanoes like Mount St. Helens. Basaltic lava flows form volcanoes with gently sloping sides. A lake of liquid lava can sometimes be seen at the top of active volcanoes like Kilauea. Sometimes the magma can flow underground to the sides of the main vent and erupt out of cracks in the ground called fissures. When lava meets ocean, the island grows, but you may not want to get too close. That steam is hydrochloric acid laced with tiny shards of volcanic glass. The Pacific plate is moving to the northwest, dragging the crust over the hotspot and creating islands as it goes. The hotspot itself might be moving too. The volcanoes on Niihau and Kauai, the northwesternmost islands in the chain, are about 5 million years old. The Big Island of Hawaii is the youngest and started forming about 400,000 years ago. It's still changing and is home to 4 active volcanoes. Eventually, the Big Island will no longer be over the hotspot, and a new island will grow next to it. But maps won't need updating for a while. Loihi won't break the ocean's surface for another 200,000 years, give or take. For Scientific American, I'm Kelsey Kennedy.
Now, along subduction zones, you tend to get more like where you have silica-rich magmas, you get explosive eruptions. So this magma is thick, it will block the tube, the vent of the volcano, and pressure can build up until, well, the top can blow off. So magmas that originate in the subduction zone are made from melting that subducting plate, so they're not very deep and they're therefore cooler in temperature. They're also higher in silica content. And due to the combination of low temperature and high silica content, these magmas are very viscous, resulting in explosive eruptions. And it turns out there's some processes involved in the formation of magma where you actually get different silica content based on the temperature, because different minerals melt at different temperatures, essentially. And so lower temperature magma will always generally be higher silica content, while higher temperature magma will always be lower silica content. So here's a video showing different types of volcanic eruptions, both peaceful and violent. The reason it's called Plinian is because it was recorded by Pliny well, both Plinies, Pliny the Elder and Pliny the Younger were involved. it killed Pliny the Elder because he went to investigate, and it sounds like he got too close and breathed in too much unfortunate stuff and died from that. It's not entirely clear what caused his death, but he went to investigate. Some of his reports made it. So here's a violent eruption. This is Mount St. Helens exploding in 1980. And it basically blew the top off the mountain. But the mountain ended up like 1,000 feet shorter. So volcanic structures are formed from that volcanic material that reaches the surface of the earth. It can create a number of dramatic surface expressions. But the type of features that form depend on the type of eruptions and the type of lava. So what kind of volcano you get at the surface is largely dependent on the temperature and the composition of the lava. So some common structures include flood basalts, shield volcanoes, stratovolcanoes, cinder cones, and calderas. And we're going to go through all of these, but flood basalts and shield volcanoes form from very thin lava that is hot and basaltic. Stratovolcanoes form from sort of medium lava that sort of alternates between violent and more peaceful, allowing them to be the most dramatic and big. When you think of the big conical volcano that everyone sort of thinks of when they think volcano, that's a stratovolcano. Cinder cones are small structures that are formed primarily of cinders. They're formed from Teflon piled up. They can form very quickly. And calderas happen when the magma chamber empties out and collapses. So fissure eruptions take place when a large volcanic volumes of lava come through long fractures along the surface of the earth, and they flood out basaltic lava. So in 2010, there was a fissure eruption in Iceland at GEOL110. I'm certain I did not pronounce that name, but that has far too many J's. So I will not attempt to pronounce that Icelandic name of that again. And in the more distant past, significant portions of Washington, Oregon, and Idaho are all covered with a series of ancient flood basalts that are called the Columbia Plateau. And these are on a scale we don't see at all these days. Huge, massive floods of lava that covered hundreds of miles that were like, hundreds of meters thick. So the basaltic lava that formed these layers was extremely fluid at a very high temperature and a very low silica content, and eventually covered an area of 576,000 square kilometers, with an average thickness of 150 meters. And this happened to several things, so there's layers of these, but these layers are quite thick. And the whole pile is enormous. So here's a short video about those flood basalts.
Two-minute geology, two-minute geology. Hello, young people. The Columbia River basalts near Quincy, Washington. We're at Quincy, Washington, but we could pick any spot between Spokane, Washington, and Seaside, Oregon to do this show. These brown layers of basalt are everywhere in the place where the Ice Age floods did massive amounts of erosion thousands of years ago. There's more than 300 layers of basalt here, 300 separate volcanic eruptions, and the stack of basalt is more than 2 miles thick in places. The lavas started erupting 17 million years ago here and flooded a landscape, buried a landscape in lava. The obvious question is, which volcano erupted? Was it Mount Rainier? Mount St. Helens? The answer is none of those. The Cascade volcanoes do not match the chemistry of these basalt lavas. These are lavas that came from the east. They erupted out of fissures, deep cracks, that emitted Hawaiian-like lava starting 17 million years ago. Fissures that formed related to the birth of a hotspot that's now underneath Yellowstone National Park in Wyoming.
They'll do this fascinating thing where they'll break into hexagons.
The present is the
from
key
the
to the
cooler.
past. To really visualize eastern Washington 17 million years ago, we need to go to Hawaii today. Those Hawaiian lavas today are the same kinds of lavas that we have here. Lava flows in Hawaii, very fluid. The most fluid lavas we have in nature average less than 3 feet thick. Here in eastern Washington, the lava flows average 100 feet thick. In Hawaii, the lavas travel on average 3 miles in length. Here in eastern Washington, many of the lava flows traveled 300 miles. And in Hawaii, 30 miles are covered by a typical flow. Here in eastern Washington, 30,000 square miles of area buried. The Columbia River basalts near Quincy, Washington. It's all out here to see. Coulees, rocks, and canyons is scenery. Right here for you and me. 2-minute geology.
So here is the Nevada del Rios volcano in Colombia. I believe this is more like a super cone. So when you have lava that's not quite as fluid as the lava that formed flood basalts, you get shield volcanoes, like the Hawaiian Islands. These are, they have gentle slopes. They sort of travel out in a curved thing. The idea was that they sort of look like a shield, the arch sort of shield sitting on the ground. And the eruptions are generally frequent, but not particularly violent. So these are the things that are sort of steadily pumping out lava. Now, stratovolcanoes are composed of alternating layers of medium and high silica content lava and tephra. So what happens is they have violent eruptions, but they erupt, though they usually erupt much less frequently than shield volcanoes. And sometimes what they have is they have more violent eruptions that then have more liquid, which throw out a lot of tephra, which gets glued down by the medium silica content lava that comes after. And most of the majestic solitary mountains of the world are stratovolcanoes. So things like Mount Fuji, Mount Shasta, Mount St. Helens, Mount Hood, Mount Kilimanjaro. These are all stratovolcanoes. Big conical mountain with fire coming out of the top in the middle of nowhere. That's a stratovolcano. Your classic volcano, when you think volcano, is a stratovolcano. So here is Mount Fuji in Japan. This is a stratovolcano. Has a caldera at top. If it erupted, it would be a nightmare. Now, some volcanoes are relatively small. These are cinder cones. This happens when a volcanic eruption is particularly high in gas content and thus emits basically just like tephra, ash, rocks and stuff, because everything cools down before it makes it to the surface. Cinder cones are relatively small. They rarely exceed 300 meters in height. They form quite quickly. There's one that formed in the middle of a cornfield in Mexico that like formed over a period of like a month or something. It was fast. And they rarely exceed 300 meters in height. So here is a short video going over various types of volcanoes.
Volcanoes act up in every possible way. Like a moody person, they can erupt in violence or steam silently, lazily creep along or self-destruct. A volcano's origin determines its temperament. Many volcanoes erupt along subduction zones. Here, the great tectonic plates of our planet's surface push against one another. Along this margin, where one plate is rolled beneath another, we find the most violent volcanoes. Explosive eruptions fit our image of a volcano. They create large, cone-shaped mountains. These erupt when magma below forces its escape. Fueled by expanding gases and boiling groundwater, the excess heat blasts through. Volcanoes like this often have alternating layers of different volcanic materials, ash, cinders, and lava. These layered cones are called composite volcanoes.
Or stratovolcano. It should end.
Hawaii isn't near the joining of two plates, but it's a hotspot of volcanic activity. What fuels it? The Hawaiian Islands are hotspot islands, created when a pool of magma breaks through a thin spot in the crust. As it burns through, the plate moves along at 10 centimeters a year. One island is carried away to cool, while the next one is created in assembly line fashion. On the Big Island of Hawaii, Kilauea has been erupting since 1983 and shows no signs of letting up. It's an example of a second kind of volcano, the shield volcano. The central crater is called a caldera. It still steams, but probably won't erupt violently. Farther out, lava oozes and flows, creating new land as it cools. The wide flow is what creates a shield volcano rather than a cone one. This new unstable bench is pure basalt. Sometimes the flows are only inches from the surface. The thick, honey-like lava, typical of Hawaii, cools into a harsh, barren environment that can take years to support life. Cinder cones are a third kind of volcano. Mexico's Paracutin is a dramatic example. Like composite volcanoes, they can be explosively violent visitors to the surface of our planet. They burst forth with enormous quantities of ash, cinders, and lava fragments. They rapidly build volcanic mountains, but never as wide as shield volcanoes or as high as composites. Cinder cone shape is determined by the size of the ejected material.
So that's a little out of date with some of the things it said. Kilauea stopped erupting and started in 1983, stopped in 2018, but then it's started up again since then. It's had a couple of eruptions since then, and it's currently erupting. But it had a short break of a year or two. Here is a cinder cone volcano. You can see that it's small and steep. I don't remember what that other one. I might have been told this one. And this is in El Salvador. And a caldera happened. A caldera is a structure that forms when you have a volcano with a big magma chamber, and that magma chamber empties out. And so you have a big empty space which collapses straight downwards, and you get this roughly circular steep walled depression at the volcano's summit, which can be up to several miles in diameter. So you get calderas from the collapse of the chamber at the volcano's summit from which lava and ash were being emitted. An example of this is Crater Lake in southern Oregon, which occupies a caldera formed by the collapse of the magma chamber of a once active stratovolcano. And here is Wizard Island in Crater Lake, which is actually a small cinder cone formed within this lake. So, some historic eruptions. Mount Tambora in 1815 was volumetrically the largest volcanic eruption to occur in written history. So much volcanic dust was put into the upper atmosphere that the sun's energy was partially blocked, resulting in 1816 being unusually cold and being called the year without a summer. The terrible weather caused by this volcanic eruption led to the writing of Frankenstein. I'm entirely serious. Like, Mary Shelley and Lord Byron and such were on vacation. The weather was awful, so they weren't doing anything outside, so they decided to have a writing contest. And out of that came Frankenstein, the first modern vampire story, things like that. Mount Pelée in 1902 was located on the island of Martinique in the Eastern Caribbean, which blasted out a deadly cloud of superheated volcanic gas and tephra that killed over 30,000 people. Paracutin in 1943 is located in Mexico. It began as hot gases were emitted in a plowed cornfield. The cornfield was destroyed as this volcanic cone eventually rose over 400 meters in height, and this didn't take very long. Surtsey in 1963 was located off the coast of Iceland. This volcanic eruption eventually formed a permanent new island in the North Atlantic. New land. Soufriere Hills in the 1990s is located on the Caribbean island of Montserrat. This volcano had been dormant for 400 years until it began spewing ash in 1995. And the capital city of Plymouth and the airport were buried in 1997. And most inhabitants left the island or moved to the north end. In 1980, Mount St. Helens, which is a stratovolcano in southern Washington state that had been dormant since 1865, blew its top. It devastated more than 400 square kilometers of area and resulted in the death of more than 60 people. It leveled the forest all around. So there's pictures of this where it was like, it used to be forested, and then after the explosion, the forest is gone and the lake is covered with, the lake below the mountain is entirely covered with felled trees. Mount Pinatubo in 1991 is located in the Philippines. It propelled ash into the atmosphere to a height of over 24 kilometers. This destroyed thousands of acres of cropland and forced the abandonment of the Clark Air Force Base. And now, why do people continue to live in the shadow of a dangerous volcano? So, for example, an eruption by Mount Vesuvius in 79 CE buried 2,000 residents of Pompeii and also several thousand residents of other surrounding towns. Yet the large and growing Italian city of Naples lies only a few kilometers from Mount Vesuvius. Part of the reason people live near volcanoes is because the soil that comes from volcanic ash is very rich and fertile, which results in extremely productive agricultural area. And also, like, these aren't common. So, the volcano doesn't explode all the time. It explodes every once in a while. And so, rare events, people are bad at dealing with the risk of. But I mean, there are ways you can deal with it as well. And then we have historic volcanic eruptions. This is some of more recent ones that have been caught on film. So these are like top 10 volcanic eruptions caught on camera.
Volcanoes are scary unless you're immune to lava, ash and falling rock, in which case you're probably not scared by volcanoes. For the rest of us though, they're pretty crazy events to witness. Most of us haven't seen a volcano up close, but thanks to other people and their cameras, we're able to see videos of their immense powerful eruptions. We have the best of those for you guys today. My name is Danny Burke and this is the top 10 volcanic eruptions caught on camera. Starting off at number 10 now, we have Pu'o'o. This is an active volcano in Hawaii, and in 2014 a lava flow started shooting out eastwards. Roads were closed off as the flow devastated everything in its path. Now, despite numerous defensive measures being taken, it seemed like nothing could halt the slow but steady progress of the lava. This resulted in this incredible footage of the lava burning through a metal fence and then right onto a road. Alright, at the number 9 spot now we have the Sakurajima volcano. This volcano in Japan erupted in February 2016 and some incredible footage was taken of it. The eruption itself was already quite large, sending lava and rock tumbling down the mountain just 30 miles away from a nuclear power plant. However, many people were more amazed at the lightning storms that formed inside the clouds. Lightning and lava, definitely a cool but lethal combination. Next up at number 8 now we have Mount Tavuva. This volcano in Papua New Guinea erupted in 2014. Some tourists were nearby and captured the footage you're about to see. They expected the eruption was going to happen at any moment. They expected that a sonic boom would follow shortly after, but maybe not as loud as this. Next up at number 7 now we have Popocatépetl. This is an active volcano located just southeast of Mexico City. It erupts every few years, and when it did in September 2017, cameras were there to capture it. The rocks it spewed out were found more than half a mile down the slope, as well as ash over nearby towns. Scientists monitor the volcano carefully as 25 million people live within 60 miles of it. A super eruption could be devastating. Alright, at number 6 now we have the Turrialba volcano. This is located in Costa Rica, and the footage you're seeing comes from an eruption in September 2016. It was caught by a research team's cameras, and the footage sped up to show you just how long the volcano was spewing out hot ash. This event consisted of 4 separate eruptions, which led to the closure of the capital city's international airport. It was reported that clinics were filled with people suffering from skin and lung irritations. Some stores even started selling kits with goggles and masks for protection. Moving on to number 5 spot now, we have Mount Shindaki. This volcano in Japan erupted in 2015. It was largely unexpected, but amazingly, an internet webcam caught the whole thing live. Huge waves of pyroclastic flows cascaded down the side of the volcano, spewing rock fragments and hot gases across the volcano's northwest shore. Japan's meteorological agency raised their alert level to 5 and ordered the island's 140 residents to evacuate. Okay, next up at the number 4 spot now, we have the Mayon volcano. This volcano in the Philippines has been known to erupt from time to time, but the most recent event might have produced the most incredible footage so far. On January 22nd, 2018, an alert level 4 was raised as Mount Mayon spewed ash 3 kilometers into the sky. The footage you're seeing right now was taken at night, where lava bombs and rockfall produced a spectacular sight. Now, to my eyes, the volcano seems to resemble something like Mount Doom more than anything I've seen in real life. Incredible stuff. Okay, moving on to the number 3 spot now, we have Journey to the Center of the Planet. This clip comes from a BBC documentary of that name, where a scientist in a protective suit ventures to the edge of a volcano's lava lake in order to try and get a sample. Things get a little bit too close for comfort when the lake starts to erupt over the edge, spilling lava everywhere. The scientist has just enough time to get out before lava flows where he was stood just minutes before. Okay, next up at number 2 now guys, we have Mount St. Helens. On May 18th, 1980, Mount St. Helens in the state of Washington erupted. It's often referred to as the single most disastrous volcanic eruption in US history. The whole north face of the volcano just slid away to expose an explosion of molten gas and rock that spread out over 11 different US states. This is the incredible footage from that day. Although some scientists were aware that the volcano was showing increased signs of activity, everyone was surprised at the sheer scale of this eruption. And finally at number 1 now we have the Kilauea volcano. Located in Hawaii, it's also referred to as the volcano that never stops erupting, and that is kind of true. The volcano has been erupting since 1983, but things picked up a notch on New Year's Eve 2016 when a lava delta collapsed, taking part of the sea cliff with it. This created a constant flow of lava into the sea below, which has been captured by a number of people, including this footage you're seeing now from the Wall Street Journal. Well, that was fascinating. I always end the video by saying well, don't I? Has anyone else noticed that? Anyway, do you like volcanoes? Did this video make you like volcanoes even more? If so, would you like a part 2 to this video? Let me know. My name is Danny Burke. Thanks as always for watching guys, and I'll see you all in the next video.
So that was all forms of igneous rock. Now let's talk about the other types of rock, sedimentary and metamorphic. So sedimentary processes, the early conception of sedimentary processes was put together by James Hutton. It was derived from his field observations of modern sedimentary processes in ancient rocks as he traveled around Scotland. So his frequent field trips in and around Scotland, he observed the normal everyday effects of water and wind on rocks and soil. And in particular, he noted that mud, sand, and rock fragments of all sizes were weathered and carried by streams. They were weathered and then eroded and carried by streams from high areas to low areas where they could form new rock. So weathering is the process of rock breaking down, and then erosion is the process of rock being carried from one place to another. And this levels off the ground in a process that's known as gradation. We'll talk more about that.
Believe it or not, the rolling countryside of Cornwall in southwest England used to look more like the Himalayas or the Alps. Mountains don't last forever. They gradually wear away at a rate of about 10 centimetres every 1,000 years. So all that's left in Cornwall today is a series of domed shapes, giving the landscape its rolling appearance. Changes in temperature from day to night and the expansion of freezing water cause rocks to wear away. When water enters a crack in a rock, it expands as it freezes overnight. When the ice turns to water and freezes again, it forces the crack open a little more. As the water seeps even further, the crack widens. This freeze-thaw action is repeated. It eventually causes pieces of rock to break off. They fall down the mountainside, where they lie as pieces of jagged rock known as scree.
And this freeze-thaw cycle is the main method of weathering around here. It's also why we have so many potholes, because we have a lot of temperature swings, so we get more freeze-thaw cycles. Same process works on the road as does work on rocks and such. So particles are weathered away by various processes. Particles that have been eroded from one place are later deposited as sediments somewhere else, usually along rivers, at the shore, or on the seafloor, because the most common thing that carries them is water. And Hutton also observed that layered rocks in the highlands that were composed of cemented sand and other rock fragments, and he called these sedimentary rocks. So sedimentary rocks are made of rocks basically glued together from bits of old rock. So most sedimentary rocks are deposited in horizontal layers or strata because, it's sediment. It settles out of the water in flat layers. And older layers were converted to sedimentary rock as they're compacted by the weight of the overlying and successively younger layers. This process is called superposition. And this principle of superposition is what allows us to date layers, to figure out how old they are by looking at like fossils in them and things like that. And allows us to date, it helps in dating of fossils and archaeological finds and things like that. So some of these sedimentary layers get pushed up by powerful forces within the earth to form mountain ranges, and then the process continues as the newly uplifted areas are affected by the weathering processes. So sedimentary rocks only compose about 5% of the crust. But they're almost entirely on the surface. So they actually are exposed over about 75% of the Earth's surface. So the Earth's crust is dominated by igneous and metamorphic rocks with a thin veneer of sedimentary rocks on top. That's only a few kilometers in thickness. And a lot of the necessities of modern life come directly from sedimentary rocks. Things like petroleum, coal, certain metal deposits. The most common type of iron ore is a sedimentary rock, for example. And many materials that are used in the construction industry, like The gypsum in drywall and things like that all come from sedimentary rocks. And some of the most picturesque spots on Earth are composed of sedimentary rocks because you can get layers of different colors, which then get eroded away and can be very dramatic looking. Because sedimentary rocks occur in a number of varieties and colors, and the Colorado Plateau of the southwestern US offers a particularly outstanding display of sedimentary rocks and their erosional products because it was a whole big flat area that got thrust upwards. So all the rivers and water sources cut deep channels through the layers of sediment, exposing many layers. So the process by which sedimentary rocks form is called lithification. The process of transforming sedimentary rocks, sediments into sedimentary rock. Basically, you can translate it as rockification, the process of making a rock. Lithy is rock. So the compaction and cementation of loose sediments are the main process responsible for lithification. So you have sediments, they get compacted together and then cemented together by dissolved minerals. So calcium carbonate, silica, and iron oxides that get dissolved in groundwater are the dominant cementing agents. And we process calcium carbonate into cement, and we want to do this ourselves artificially. Now, concrete is basically artificial sedimentary rock. We just process the calcium carbonate into something that reacts with water very quickly to form concrete instead of having to wait a very long time. So basically what happens, the sediment piles up, it gets compacted, so all the gaps are squished out, so everything is very tightly packed together, and then dissolved minerals form in these, crystallize out in these gaps and glue everything together. So the weight of the overlying sediments force the sediment grains together. This causes physical changes in the process of compaction, and then dissolved minerals precipitate out of groundwater, and their growth glues the sediment grains together into a solid rock. So sedimentary rocks can be classified according to their origin, the origin of their constituents. There's two main types. There are clastic or detrital sedimentary rocks and chemical sedimentary rocks. Plastic sediments are just broken up bits of rock. So these are things that originate from solid fragments, detritus that erode from pre-existing rocks. This makes things like conglomerate, sandstone, mudstone, things like that. They are bits of existing rock that are glued together. Chemical sediments originate as dissolved minerals in solutions. So these are minerals that dissolved away and then reformed, got pulled out of solution in some way. This could be the water evaporates and they precipitate out of solution, or living things use them, turning them into hard parts of their bodies, and they fall out of solution that way. So clastic sedimentary rocks are classified according to the grain size of their components. If the grains are really tiny, and so you started with mud, you get something like shale or mudstone. So very fine grained particles that were initially mud. Sandstone is composed of sand-sized particles. Conglomerate is composed of rounded pebbles from the bottom of a stream. And breccia is composed of angular pebbles that didn't travel very far in a stream. And clastic rock particles are generally held together with either calcium carbonate, which dissolves readily in groundwater, or silicon dioxide, which doesn't dissolve as readily but is all over the place. So this is a short video about the formation processes of clastic sedimentary rocks.
Clastic rocks are the most common type of sedimentary rocks found on Earth's surface.
This mini video describes how these rocks are formed.
Check out this related video for a discussion of the classification for all types of sedimentary rocks.
There are 3 steps in the formation of clastic sedimentary rocks. Clastic sediments are composed of fragments of rock. In fact, a clast is a technical word geologists use to describe a rock fragment. These fragments weathered from pre-existing rocks to form sediment of various sizes. This sediment is then transported away from its source area, and finally it is deposited and converted to form a new rock through lithification. So let's take a closer look at these processes, starting with the breakdown of rocks by weathering.
Rocks break down on the Earth's surface to form sediment. The resulting rock and mineral fragments may then be further physically or chemically weathered to form even smaller grains or other minerals.
For example, individual feldspar minerals are weathered out of this igneous rock. Notice the grains of sediment at the base of the outcrop.
Sediment like this is then eroded by transportation agents such as streams, winds, and glaciers.
This river in Alaska is carrying a high sediment load as reflected by the muddy color of the water and the sand and gravel bars in the stream channel.
Much of western Oklahoma and northern Texas lost their topsoil to winds during the Dust Bowl era of the 1930s, and we see similar dust storms today in drought-stricken western states.
Elsewhere, dust and sediment from the Sahara Desert may be transported across the Atlantic Ocean to Central and North America.
Finally, sediment of all sizes is transported by glaciers. For example, the dark surface of the Reed Glacier in Alaska reflects that sediment is exposed as ice melts. If we look closely at the glacier, we can see layers of sediment encased in the ice.
The last stage in the formation of clastic sedimentary rocks occurs after the transporting agent loses energy and the sediment is deposited.
As more and more sediment builds up, the material at the base of the pile is compacted. Compaction squeezes out spaces between grains and pushes the grains closer together. Finally, chemicals precipitate out of water to cement the grains together and form a rock.
These processes result in sedimentary rocks like shale, sandstone, and conglomerate.
So as we finish up, how confident are you that you can meet the learning objective?
So here's an example of like, they vary from very fine grain, like shale here, then we get medium sandstone, and then we get something like breccia here, which is more, or conglomerate, which is more larger, coarse. So gravel has a grain size of greater than 2 millimeters. This creates conglomerate if it's rounded pebbles, or breccia if it's angular pebbles. Sand is from 1.6 to 1/16 to 2 millimeters. This creates sandstone, and less than 1/16 millimeter is mud, and that creates shale. Chemical sedimentary rocks get divided into 2 types, organic and inorganic. And in both cases, the chemical sediments are composed of minerals that were transported in solution to their eventual deposition site. Organic chemical sedimentary rocks, those minerals pass through living things. Inorganic ones, they didn't. So inorganic sediments, you get things like inorganic limestone that's made of calcite, evaporates like halite and gypsum, dolostone, which is made of dolomite, inorganic chert, which is chemically precipitated silica. This is like flint. Chert is the more general term. Flint is a little more specific. Biogenic limestone is calcium carbonate remains of marine creatures like algae or Foraminophilia, so basically tiny living things that had calcium structures. Biogenic chert is silica-based remnants of marine organisms, radiolari diatom sponges, and coal is the compressed remains of terrestrial plants. Organic sediments are formed largely by the action of organisms that remove the minerals out of solution. So many large and microscopic organisms in the ocean extract calcium carbonate out of seawater to construct skeletal and shell material. And as these organisms die, their hard parts come to rest on the bottom and eventually lithify into organic limestone. So here is an example of that with the White Cliffs of Dover, which are chalk deposits made of tiny dead things. And coal is not formed from minerals carried in solution. It's still classified as an organic sedimentary rock. It's formed from the lithified remains of ancient plants. So coal is one of those things, it's not technically made of a mineral, but we consider it a rock. Inorganic chemical sedimentary rocks are commonly formed by the evaporation of water. So as the water evaporates, dissolved minerals in the solution precipitate out. So these are things like halite, rock salt, gypsum, and various cave deposits of calcium carbonate. So stalactites and stalagmites are all formed from evaporating groundwater depositing calcium carbonate. We don't have time for the next video. You can watch it on your own, but it goes over chemical sedimentary rocks. And many inherent characteristics of sedimentary rocks are used by geologists to get a better understanding under the conditions where these rocks were deposited, including characteristics such as rock color, grain rounding, grain sorting, bedding, fossil content, ripple marks, mud cracks, footprints, and even raindrop prints within the rock reveal the rock's origin and history. So the color can be quite varied. Gray shades are common in sedimentary rocks. This indicates the rock was deposited in shallow, well-aerated marine waters. Yellow, brown, and red indicate the rock was deposited on land. Let me just something. I'm not counting for no reason. Oh, the 21 quiz. Okay. We can actually do this. I am panicking for no reason. I thought we needed to get further. In that case, we will watch this and be done for the day. And then we will continue on and start chapter 23 next time. I misremembered something.
Chemical sedimentary rocks are one of the three major types of sedimentary rocks. This mini video explains how they're formed.
Imagine you took a tablespoon of salt and dissolved it in this small beaker of water. Then you added the water to a pan on the stove and cranked up the heat.
As time passed, in this case about 4 minutes speeded up, the water would gradually evaporate and the salt concentration in the remaining liquid would get progressively higher until the salt began to precipitate out of solution.
You can see the salt crystals forming here and along the edges of the pan. Eventually, when all the water is gone, the pan will be coated with the same salt that was originally dissolved in the water.
Essentially the same thing happens in nature, just not as quickly. This occurs when water in isolated seas or lakes evaporates, leaving behind dissolved minerals.
For example, ancient Lake Bonneville covered much of Utah 10,000 years ago. Most of the lake dried up, leaving the flat lake bed covered in a layer of salt.
Because these chemical sedimentary rocks form by evaporation, they're known as evaporites. As seawater evaporates, the concentration of salts changes and the different rocks are formed.
Gypsum will precipitate first, followed by rock salt as salt concentrations increase in the shrinking water body.
Minerals are also dissolved in lesser concentrations in groundwater and freshwater lakes and rivers, and are also concentrated in hot waters associated with thermal features such as hot springs and geysers.
Precipitation in these cases occurs when there are small changes in water chemistry.
For example, water evaporates in caves to leave behind limestone deposits. Each water drop loses carbon dioxide and deposits a film of the mineral calcite, which eventually builds up to form features such as these stalactites.
Gases are also lost as warm groundwater comes to the surface and minerals precipitate to form travertine, a type of chemical limestone which forms these terraces in association with hot springs in Yellowstone National Park.
Elsewhere, silica-rich groundwater may replace limestone to form irregular chert nodules, or produce chert when it precipitates in buried trees to form petrified wood.
So to summarize, chemical sedimentary rocks are typically formed as a result of evaporation or precipitation from mineral-rich waters.
Finally, how confident are you that you can successfully meet the learning objective for this lesson?
So that is where we're going to stop for today. I'll see you all for the lab. The previous lab is due. If you want to see, videos of a really dramatic case of chemical sedimentary rock, look for videos of, I think it's called Witch's Cave. It's in England. There's that travertine forming, but it's forming from water dripping over the front of a cave. So people are hanging various things. So you see like teddy bears turned to stone. and stuff. Have a good day. Sorry about the weird panic.